So this would be a really wonderful way to program, but there's a problem with it. It might be conceptually nice, but in fact, we're not going to be able to put the entire universe into our computers. So there is a bit of a problem. Actually, the most serious problem is that if we could do this, then we could write code like this. Look, maybe we're not quite sure what to do. So let's try two different methods and get two different universes. Now, maybe this first method fires the missiles, and this second one doesn't. But we're not sure which will give the best result. Let's just try both, look at the universes that we end up in each case, and then, if W1 is nicer, pick that one. Otherwise, pick the other. It would be great. But tough on the compiler writer. So what are the problems? Well, we can't duplicate the real world, of course. And even if we could, we can't then discard the real world if we find that we don't like it. And we would need to be able to do both of those things to allow this kind of programming in general. So what we have to do, of course, is if we want to do this, we need to make sure that programs use the world linearly, so that there's only one universe state at any one time. And I think you've been studying linearity earlier in this school, yes? Yeah. So we can do this, but we have to make sure that we don't duplicate or discard the universe while we're at it. And it turns out we can do that with a monad. This is what the I/O monad, so-called, in Haskell does. It enforces linearity on the world. So it's essentially the same as the state monad that we saw earlier. You can think of it as state world. We just pass the entire world in, return the entire world out. But if you think of the definitions of return and bind, I wrote them very carefully so that we never used the same state twice, and we never discarded a state. So return and bind make use of the state in a linear way. So now, if I make the I/O type abstract, so that the programmer can't actually write these world-to-world functions, but can only construct them using the I/O monad, then I can make sure that all of those functions really do treat the world in a linear way. Return and bind have the right kind of properties. I also have to make sure, of course, that all of the primitives that I provide that can construct this abstract type have the same property, that they don't duplicate the world. But we can make sure of that. So this is the way that Haskell input-output works. All values of type IOA use the world in a linear way. Haskell main programs don't do input-output, they just return an I/O value. The programmer can't actually call these functions. Why? Because the programmer can't get hold of the world. The programmer has no parameter that could be passed to these things. But the runtime system can. And the runtime system actually really does call these functions. It doesn't pass the entire state of the universe as a parameter. It passes a token that represents the entire state of the universe. But it really does pass something representing the world in, and it gets something representing the world out afterwards. And then, when the Haskell program reads or writes a file or whatever, actually the runtime system knows that this is constructing a new world, but that new world is going to be the only existing one, and so it's okay to actually perform the side effect on the real universe. So, first of all, this explains something that beginning Haskell programmers often struggle with. They say, I've written my code, and I'm getting an IOA, but I want the A. How can I get rid of that pesky IO type? And the answer is you can't, because you don't have a world to pass to the function in there. What you have to do is use the bind operation to make use of the value in the pesky IO type. So I like to think of Haskell as a mafia boss. The Haskell programmer keeps his hands clean. He doesn't perform any side effects, and yet the dirty work still happens down there somewhere. And, you know, it wasn't me. It was the runtime system what done it. Amazingly enough, it may not work for mafia bosses, but it works for Haskell programmers. And as a result, Haskell code is referentially transparent. It has all the nice properties a functional code should have, but Haskell programmers can still cause side effects in the real world. The I/O monad is one very, very important application of the monadic idea. You don't want to know how we did input-output in Haskell before we had it. Believe me. But it's just one application of monads, and although it's a very well-known one, it's not the one I want to focus on in these lectures. So I won't say so very much more about it. Okay, so where are we now? Well, we've introduced the monad class. We've got these operations, return and bind. Every monad has to support those. And then we've got a bunch of examples, and there are many more. Different types that can implement those operations, but also do some other stuff. Like in my state example, I had tick to increment a counter. In the maybe example, then nothing represented failure. In the random example, then I had generate. And in the I/O example, then I showed you put string. And of course, there are many other such functions. So we've got some common operations over here that all monads support. And then, ooh, oh, how did I do that? How did I do that? I'm just making sure you're awake here. So then we have a bunch of special operations that are different for each monad. Now, the special operations, they're actually the whole point. The only reason for using the maybe monad is so that we can return nothing to represent failure. So you might say, well, how much do we gain really from having these common operations on the left? Is there much value in using the monad class rather than just, you know, coming up with one's own interface? Because what we're doing here is we're saying we're providing, for example, random generation, and a part of the interface will be standardized. It'll be the monad interface, while the other part will vary depending on what the monad is supposed to do. So what's the value in having a common part of the interfaces? Really, return and bind, they're just doing plumbing. They're plumbing our code together. Why is it a good thing to use the same plumbing for many different applications? Well, there's two big advantages. First of all, it means that we can write libraries that use that plumbing and work with all monads. And such libraries represent work that the individual monad implementer doesn't have to do. And secondly, monads are so common in Haskell programs that Haskell provides some syntactic support for using them. And if they weren't common, if there weren't many examples, then there'd be no point in doing that. Okay, let's talk briefly about some of the libraries. The most important one is called control.monad, and it defines a whole bunch of functions that plumb things together in a way that's independent of what the monad is actually doing. Here's a nice one, lift M2. What does that do? Okay, so what the type says here is that you can use lift M2. Not good. You can use lift M2 for any monad. It takes a function with two parameters on values and converts it into a function on computations. So you can give it a monad that delivers an A and a computation that delivers a B, and you get a computation that delivers a C. Yes. On Saturday. So it's easy to define using bind. Here's the definition. First of all, we'll take A. Oh, I can't reach. Damn. Oh, it's okay. First of all, we take A, we compute A and use the result. Then we compute B and use that result, and then we just call F, giving it A and B, and return that. And obviously, this for any number of arguments. For example, for one argument, here's lift m1. It's actually just called lift m. Oh, look. Look at this type. It's the same type as fmap. So that tells us that we're going to be able, if we've got a monad, we're always going to be able to write an instance of the functor class. So monads are functors. That's nice. And here's another useful function. You give it a list of, for example, maybes, and then it performs these, it combines these computations in sequence using bind, and gives you a computation of a list of A's. So I hope you can see that there will be lots and lots of examples of functions of this kind that you can define, and there are far more in the libraries than it would be interesting to go through. But there are a lot of them. And all of those things are things that you then don't have to write when you're using maybe or state passing or random or whatever. Here's the definition of sequence. Isn't that short and sweet? We're taking here the cons operator. This is Haskell's cons, function of two arguments. We're lifting it to work on computations. Then we're using fold_r or reduce to use that to combine all the elements of this list, and at the end we just return the empty list. So that's a nice one-line definition of this sequence function. What about the syntactic support? Well, here, instead of writing what I showed you above, which I read to you as compute MA, use the result of MA and call it A, use the result of MB and call it B, we just write the thing that appears below, which has a deliberately imperative look and feel. So we'll read this as do, let A be the result of MA, let B be the result of MB, and return FAB. But it's very, very simple to rewrite do back into the functions we've already talked about. If we have a do with a pattern drawn from an expression followed by a block, that means take the expression and use bind to use its result in the block. The notation also allows you to leave out the pattern, which means you simply don't care what the value is, you only care about the effect. And then finally, if you apply these rules repeatedly, in the end the block will just have a single expression in it, and then you can discard the do. That's really all there is to it. So do gives an imperative look and feel, but it's very, very simply translated into the underlying functional code. So if I go back to zip tree again, let's see how this new stuff helps me simplify my code. Well, if we look at the branch case, what are we doing there? We're doing two recursive zips and combining the results. So I can replace that by a lift m2. The branch constructor is the function that I use to combine them, and so I can just say lift the branch constructor to work on monadic computations and give it the computations of the left and right subtrees. If I go back to node numbering, once again, the first case just does two recursive computations, combines the result with branch. That's lift m2 branch as well. And the second case just lifts the leaf constructor to work on the computation of the tick. So I can write the code like that. And now the structure of the code is almost indistinguishable from the very first code I showed you, which I couldn't write because Haskell doesn't have, because Haskell is a purely functional language. So by using the libraries that are available, one can write code in a very, very natural style. Okay, so I introduced this do notation, and bind was a binary operator, but do is kind of n-ary. So that begs a question, doesn't it? If I write this thing on the left, there are really two binds in there, and the translation I showed you says that that means the same thing as the thing on the right. But what about this? This would be another way of achieving the same effect. So the top box there brackets the second and third things together. What if I bracket the first and second things together instead? Okay, so in this case, we compute x from E1, and then the result is E2, which we bind to y in E3. Now, obviously, if x appears in E3, then these two cannot be equivalent. But let's assume that it doesn't. Should those two ways of bracketing the do give the same result or not? And there are other questions we can ask, such as, suppose I compute an x from E and then just return it. Is that the same as E? Suppose I start off my do block by just returning x and calling it y. So I'm really just renaming x there. Can I discard that return? So the answers to all of these questions, we would like to be yes. We'd like to be able to reassociate the commands in a do block. Why? Well, if you've got a do block with a number of commands in it, you might want to factor out some of them in the middle and put them into a separate function. And in order to do that, we need to know that do behaves in an associative kind of way. So just as the associativity of plus, for example, is important to us when we do mathematics and we write down polynomials without worrying about how they bracket, so these equivalences are important to us when we write monadic code with more than two commands in a sequence. And they might not hold necessarily, but in fact we say that a monad is only a monad if it satisfies the monad laws. And after desugaring those things that I showed you on the previous slide, this is what they say. The first one is a kind of left unit law. It says that if you return x and then use that result in f, that's the same as just passing x to f directly. The second one says that if you take m and then use its result just to return it, that's the same as m. And the third one is a kind of associative law that says that if you take m, use its result in f, and then use the result of that in g, that is the same as taking m, using its result as x in f of x with the result used in g. So it's very important that these three monad laws hold. Do they hold for our monads? Of course not. Here's a counterexample for the state monad. So this is an example of the left unit law. So return x followed by anything should be equal to that thing applied to x. Now what I've put on the slide is an underlined vertical bar. It's supposed to represent bottom, the non-terminating value. So please think of it that way. I couldn't find out how to put a proper bottom on the slides. Okay, so if the monad law holds, then it should hold for bottom too. But if we look at the bottom of the slide, we've got non-termination applied to x. That's equal to non-termination, of course. If we look at the top, let's unfold the definition of bind. For state S, that looks like this. And now, for the state monad, return xs just returns x and s as its result. So x prime and s prime are the same as x and s. So that's equal to this. And now, once again, we've got bottom applied to something. That's just bottom. So the left-hand side of the law is equal to lambda s bottom, and the right-hand side is equal to bottom. Are those equal? Yes. Actually, my Haskell compiler supports seek.
That's true, but that's the problem, not the statement.
They're not equal. And you can easily write a Haskell program that distinguishes one from the other. So, you know, does the law hold? Well, strictly speaking, no. Here's another example. I showed you the random monad. What about these two? These two should be equal by the right unit law. First one just says, okay, take the seed, generate generate a number up to 5. The second one takes the seed, splits it, and uses the first seed that it gets to generate the same random number. And then it just returns that. Obviously, these two generators will actually do the generation with different seeds. So if you take the same seed and you pass it to the first and to the second, you will get different results. So are these functions equal? Well, obviously not. But I mean, you objected already, and you might object to this one too. Are they equal? Yes, near enough. So in the first case, then I could only break the law by introducing partial values. And usually we're more interested in total values. When we prove things about Haskell programs, we often ignore the difference between lambda x bottom and bottom, for example. And indeed, you can only observe it if you do some kind of funny stuff, and arguably you deserve what you get. So we actually wrote a POPL paper a few years ago whose title is Fast and Loose Reasoning is Morally Correct. And what it shows is that actually you can do this stuff and you won't go too far wrong. So we can reasonably ignore those differences. And in the case of random, here, these are clearly different as Haskell functions. But what does it mean to say two generators are the same? Does it mean that if you give them the same seed, they'll give you the same random data? Or is it more interesting to say they generate data with the same distribution? I think the latter is the interesting thing to say. And in that case, these two generators are equivalent. They'll give you the same distribution. For a particular seed, they'll give different results. But nevertheless, if you refactor your program and you replace the second by the first, you're not introducing bugs. So, in fact, in Haskell, we have to consider the monad laws up to some reasonable equivalence. And for a reasonable equivalence, the examples that I've shown you really do satisfy the laws. But if you were to try and prove that formally, then you would need to formalize what that reasonable equivalence is. Okay, so rather than prove them, I want to show you a bit of fun that I had preparing these lectures. I thought, let me test the monad laws. And I can do that using QuickCheck, which is the testing tool that I've been working with for the last decade or so. So, a two-slide introduction to QuickCheck. What does it do? Well, it tests properties which are written as monomorphic functions. Here are a couple of examples. I've written a type signature on the first line, which just constrains the type so that they are monomorphic. That's necessary because QuickCheck is going to generate arguments for these functions. And in order to generate a type, we need to know which type it is. So the two properties take an argument and return a Boolean value. And they're intended to mean a kind of universally quantified property. So that first one says that for all lists of integers, x's, if you reverse x's, you get the same result. That's not true. The second one, though, says that if you reverse the list twice, you'll get the same result. And this one is true for total lists. But you know what? We're only going to run tests with total lists. So that property we're going to consider true. So QuickCheck then generates random arguments for these properties. It just calls the functions. And if they always return true, then the tests pass. And if one of them returns false, then it's a counterexample and it's displayed. So if I take prop rev, the second one there, and test it, it'll pass any number of tests. If I take the first one, then it'll rapidly fail. And you can see it says, after 4 tests, that's 4 random tests, and 2 shrinks. What are the shrinks? Well, QuickCheck also simplifies a failed test to produce a minimal counterexample in some sense. And in this case, the counterexample is 0, 1. So actually, knowing that it's minimal gives us a lot of information. We can tell that, first of all, it's clear that if I reverse this list, I don't get the same result back. So this is a counterexample to reverse x's equals x's. It's also the smallest possible one. if you've only got one element in the list, then reversing it will give you the same list back. So you need at least two elements. If they were both 0, then reversing the list would give you the same thing back. So 0, 1 is a minimal counterexample. Okay, so how does QuickCheck do this? Well, it needs to be able to generate arguments to properties. And this is done using Haskell's overloading, using a class called arbitrary. How do you make something a member of the arbitrary class? You provide a definition for arbitrary that is a generator for A's. And what's gen? Well, it's pretty much the same as random. And we also need to be able to display the counterexample. And that means it has to be in another class called show. So there's a problem here, and that is the monad laws quantify over functions. But functions are not printable. So we have a bit of a problem in that we can't use functions as property arguments. But there is a solution to that. QuickCheck provides another kind of values called funs, which are printable and contain a function. So, in fact, something of the form fun and then something and f would be an example of an element of the type fun AB, and f there is a true function from A to B. So now I can write my properties like this. Here are generic versions. Okay, so as the property arguments, I'm using these special QuickCheck fun values. The left unit property then says that for any x and any function f, return x bind f is equal to f of x. The right unit law says for any m followed by return is m. And then this is the associativity law. Once again, we're quantifying over two functions here. But otherwise, the law is exactly as I showed you before. And now, to test those laws, I have to pick a particular instance to test them at. So here's a property that I could actually pass to QuickCheck that tests the associativity of the bind for the maybe monad. And I have to write out its entire type, which is a little boring, but there we are. So m is a maybe integer. Then the next argument is one of these fun things, representing a function from integer to maybe integer. Third one is same, and then the result is a bool. But the actual definition of the property, we can just reuse the generic one. So I've chosen integers as test data here. Integers make very good test data for this kind of generic property. If there's a counterexample, very often you can find one that uses integers. So now, if I QuickCheck that, QuickCheck will say the test pass. Okay, so it's always more interesting to run tests that fail. And unfortunately, maybe really is a monad. So those tests will all pass. But I could, of course, sabotage the property to see what happens when it fails. And I did this earlier. One way to sabotage it is the associativity law has these two functions, f and g. What if I swap them over on one side of the equation? That should give me a property that's false, right? So I just want to show you what happens in that case. Here's the output. Very quickly, QuickCheck finds a counterexample. And remember, the arguments to the property were the initial computation m, that was just 0, and then the functions f and g. And you can see it's not so surprising, perhaps, that if f is the constant function that returns just 0, and g is the constant function that returns just 1, then it breaks the monad law to swap them over. So what I wanted to show you here is that we can actually test these laws, and we get very nice counterexamples that show us the simplest functions that you need to make those things break. And I hope that you will have some time to look at some exercises that I prepared earlier. Testing monad laws on monads that work is a worthy business, but it's not so very much fun. But if you get to the last exercise there, then you'll get some quite interesting counterexamples of this sort. Okay, well, I refer to the exercises. We don't have any exercise sessions for these lectures, and I realize that you have almost no time. to do anything apart from listen to people now for the next couple of days. But I hope that you will have a chance, anyway, to take a look at some of these. The exercises look quite long, but they're not. They only look long because I have included code that you can copy from the exercise into your own file, and then what you actually have to do is something quite simple in each case. But it would be quite valuable if you were able to download the exercises from this URL and try them out before tomorrow, because they will introduce some of the topics that I'll be talking about tomorrow. And I have even succeeded in stopping with more than 10 minutes to spare. So if you're quick, you can get through the exercises now. I had one or two questions during the talk, but I'm very happy to.
So I've seen this before in your test for associativity on the slide. Maybe right before this. Oh, okay. Yeah. So is testing maybe integer good enough for testing the monad maybe? It's like that's just an instance.
Yeah, well, in practice, my experience is testing with integers is enough. Jean-Philippe Bernabe of Chalmers has developed a theory that can tell you which type is provably big enough to contain any counterexamples you might want, using parametricity. But in practice, I found integers are great for testing, but occasionally pairs of integers. And that's if you're testing something which maybe is true for totally ordered data, but not for partially ordered data, then using pairs and using an order vector is partial order.
So we don't have to worry about the property that you say integer leaking into the composition test.
It's not a big problem in practice.
So one of the things like really cool things, are there any disadvantages of using maths? Practical or theoretical?
Yes. Yes, there are. So not all. A monad represents a kind of notion of computation, you might say. Not all notions of computation can be represented as monads. And in some cases you can, but it's very inefficient. So there are cases in which you might want to choose a different interface. And I will be talking about some of those on Saturday. But monads have taken us quite a long way. So I think the examples where monads work are many, many more than the examples where they don't.
Not so much put your actual Haskell files on your website because I can't copy and code from the PDF.
You can't?
No.
Oh, dog.
Wait, someone can?
Okay.